Elon Musk proposed a Hyperloop, an alternative form of transportation, a modified, alternative to a traditional high-speed monorail or bullet train. And it involves these two parallel tubes that have reduced pressures. There would be pumps that pump out air pressure so that there would be not a perfect vacuum, but almost a vacuum. And most of the earthly atmospheric pressure would be removed. And I was curious as to what magnitude this really involves in terms of like number of moles of gas that have been excluded, the size of the surface area, like how much area there actually is on the inner tube, and also what the volume is of one of these tubes. So his proposal suggests idealizing it as a big cylinder with 563 kilometers of length, or 563,000 meters. The proposal also says the inner diameter, the inside of the tube, would be 2.23 meters. And you can use this information to calculate the volume of the tube by using the formula volume of a cylinder equals pi r squared height, where the length is the height in this case. And we did this in a prior video and we got 2.2 billion liters of volume. And my question is, using the ideal gas law, can we figure out how many moles of gas there would be in this tube at reduced pressure? So to do this, we need to figure out what the pressure in the tube is going to be, what the volume is going to be, and what the temperature is as well. And the reason why I'm saying this is because we can actually solve for n by dividing both sides by RT. So if I divide both sides by RT, I end up getting that n is equal to this side, because I end up canceling out the r and t factors here, so I'm just left with n. I'm going to flip this around and put the n on the left hand side, and I'll put this stuff on the right hand side. Yeah. So n equals PV RT, or PV divided by RT. And for this to work, all the units have to cancel out, so I'm just left with moles. So what I'm going to use is the way really to do this is to kind of figure out what units you already have, and I guess sort of come up with a bill of different units. So P, V, R, and T. For pressure, the proposal that Elon Musk gave says that the pressure is going to be 0.75 torr. And for volume, we already calculated it to be that. So it's that many liters. And for temperature, we can calculate this to be Kelvin. So we'll work on this. It's a little bit unclear. So if I was to have this tube going through Central California, Central California has different temperatures, right? It's not like a constant temperature. Sometimes it's really warm, sometimes it's really cold. And inside of California, it's not as temperate, it's not as mild as the coastal areas. So when you think of California, you might think of Los Angeles or San Francisco, but I assure you that stuff inside this tube is going to be much hotter or much colder than San Francisco or Los Angeles, depending on the temperature. Like depending on what time of day it is, or depending on the season. So I would say that for temperature, I'm going to have some kind of temperature extreme, just to like think about what the range would be. So I'm going to say either 95 degrees Fahrenheit for a hot summer day, or how about 35 degrees Celsius for a cool, almost freezing night in the winter. Okay, so if I have those two temperatures, I can't just use Fahrenheit with the ideal gas law. The ideal gas law uses Kelvin, so I need to convert these to Kelvin. And the way I do this is I can convert Fahrenheit to Celsius using the following equation. So what I have to do is subtract 32 from the Fahrenheit temperature and then multiply by 5/9, and that'll give me the temperature in Celsius. And Kelvin is just 273.15 in addition to that. So I could actually just make a small modification to this equation, and I would end up getting Kelvin from Fahrenheit. So Kelvin is just the Celsius stuff plus 273.15. Okay, so if I was to plug in these numbers for F and then crank out the math, I would end up getting Kelvin. So I can do that using Excel, and I think I'll switch to Excel at this point. So I can have like a hot scenario here and a cold scenario. And in the hot scenario, what I'm going to do is just reproduce the volume that we calculated in an earlier video. The pressure in the tube is 0.75 torr, as I mentioned before, and the pressure can be converted to atmospheres by just dividing by 760. So remember that 1 atmosphere is equal to 760 torr. So if I divide the number of, or the pressure value in torr by 760, I'll get a pressure value in atmosphere. And 95 degrees Fahrenheit, well, if I was to take that number, subtract 32 from it, multiply it by 5/9, and then add 273.15 to that, I would get it in Kelvin, and that's what I did here. So 95 degrees Fahrenheit is 308 roughly degrees Kelvin. For the gas constant, I decided to use the one that has the appropriate units, and I'll show you why on the board. So N equals PV over RT. So we had pressure in ATM, and we had volume in liters, and we have R, we have temperature in degrees Kelvin. So all I'm doing is replacing these variables with our converted units. I want N to be moles at the end, so I need to have 1 over R have the units that cancel all these units, ATM, L, degrees Kelvin. So I need to make this a capital K. It always comes out looking like it's lowercase. So I need a unit or units that will cancel these and leave moles. So I need to have moles inverse moles in the bottom, right? Because I need those moles to come on top when I'm done. And I need to have ATM to cancel all the existing stuff from the other units. Let me drag that down. And I need to have liters. And I need to have inverse Kelvin, right? So I'm running out of room here. Degrees Kelvin -1. Yay. So that if I was to actually like flip this thing over, when I'm dividing by a number, I can multiply by the reciprocal. It's the same mathematically equivalent operation. So if I was to multiply by the reciprocal, I would just move all these terms to, or all these factors to the top, and then change their exponent sign. So it would be all this stuff, just copy it, and then change the sign. So instead of -1, it's just regular just moles factor there, and all this stuff's got to change. So ATM becomes to the -1, liters comes to the -1, and that -1 that we got earlier, 4 degrees Kelvin, that factor goes away. That seems pretty fancy, but it's not. What I'm doing here is I'm saying, well, I know that this thing has to have moles at the end, so I know that it has to have inverse of whatever it takes to cancel these units plus inverse moles, and that's what I have. And right now I'm just showing you how they actually would cancel out. So let's check this out. So Kelvin cancels, liters to the -1 cancels liters, ATM to the -1 cancels ATM, and I'm left with moles. So actually, this thing on the bottom is what the units we need for R. That's what we need. So I can look that up, and I end up getting this for R. If I look up the gas constant for those units, liters, atmospheres over Kelvin over moles, I get this number, 0.082057, whatever. And I can use Excel to make my life a lot easier. And all I need to do is multiply pressure and volume and divide by temperature and the gas constant. That's what this equation is. And I end up getting this number. And that should be in moles. So I need to round this number. So let's take this to the board and round it to the right number of sig figs. So let me clear some space. Okay, so let me see if I can make that prettier. No, apparently not. Okay, so this has way too many sig figs because we actually started with a factor. The pressure factor, if you remember, was 0.75. 0.75 has 2 sig figs. So this volume, we didn't round it yet, but from a previous video, it has 3 sig figs once you actually round it out. The pressure has 2 sig figs, and the temperature, if we were to work through it, it would have 3 sig figs once you go through all the steps. Let's see here. So when we did the temperature calculation, we subtracted like 95, we subtracted 32 from 95, and then we multiplied it by 5/9 and added 273.15. When you do the addition and subtraction step, you take the most accurate significant place of the least accurate number. So like this has 2 sig figs. When you do subtraction, there's still 2 sig figs. You multiply by 5/9, which is a like theoretical constant. It's a definition. So you don't actually say that that has some number of sig figs. It has infinite sig figs. So it'll still be stuck with 2 sig figs. And that has like a place that's accurate to the ones digit. So when you add the 273 to that, it's going to end up being accurate to the ones digit. So when I look at the temperature, this should be rounded to 308 for sig figs. So I can actually do that. Okay, and then this would have been 3 sig figs. There we go. And this starts with 2 sig figs, and we use some definitional constants to convert it, so this has to be also 2 sig figs. Okay, 3 sig figs, 2 sig figs, 2 sig figs. This has 1, 2, 3, 4, 5, 6 sig figs, which get overwhelmed by the sig figs. Like the 2 sig figs are going to limit us. So we need to take our answer and round it to 2 sig figs. So we'll actually have to round it to 80 or 8.6 times 10 to the 4th. I'll show you how to do that. So we have to round this thing to 2 sig figs. So I'll get this into scientific notation, which will allow me to preserve sig figs. 1, 2, 3, 4. So to get this into scientific notation, I have to move the decimal point 1, 2, 3, 4 places. So that's 8.6 times 10 to the 4th moles. So for a hot day, 95 degrees Fahrenheit in California, the pumps in the hypertube have to keep out lots and lots of air pressure. And if the tube is not refrigerated, this is the number of moles that you would estimate would be inside that tube at reduced pressure. We can repeat this in different scenarios and start thinking about what this means. So if I repeat this calculation for different pressures and different temperatures, I find that there are huge differentials, huge changes in the number of moles that are present under vacuum, under the reduced pressure versus just regular 1 atmosphere. So for 1 atmosphere, this giant tube would hold 8.7 times 10 to the 7th moles of gas. This is reduced like 1,000-fold using the like various vacuum pumps that the tube is going to have by a factor of 1,000, and it ends up being, when you calculate it out, 8.6 times 10 to the 4th. So this change by 3 factors of 10, that's a factor of 1,000. That comes from 1 atmosphere being 760 torr. So as you can see, if you divide this thing by 1,000, that would get you 0.76, which is pretty close to 0.75. So this is a 1,000th of the pressure on Earth. Mr. Musk made a joke inside of his proposal. I'm hoping it's a joke. Let me see if I can find it. Yeah, Mr. Musk made a joke about this, saying that the pressure inside the Hyperloop is about 1/6 the pressure of the atmosphere of Mars. I don't live on Mars, and neither does Mr. Musk. He may aspire to live on Mars, but he does not. He lives on Earth. He deals with pressures of about 760 torr, 1 atmosphere in his everyday life, and so do I. And the Hyperloop would involve about 1,000th of that pressure, not 1/6. So this is a huge differential that's probably going to be very difficult to implement on a large scale. And that's true whether or not it's cold or hot outside. It's still a factor of 1,000. I think that's going to be technically challenging. I really do. So I hope that he can do it. It'd be really neat if he could, but I'm not holding my breath, and I couldn't hold my breath under these pressures either, because this is like way too much of a pressure differential. If I held my breath with that kind of pressure outside, I would die. My lungs would blow up. And bad choice of words. Okay, in another video I will talk about how to think about how much mass this is in terms of just everyday air. Like how many moles of gas, like what is that weight? What is that mass in terms of nitrogen and oxygen in the air, and argon and CO2 and methane?